Hi, this is Mrs. Verbal. This is Chapter 11, Stoichiometry Part 2. So today I'm with my friend the mole again, and we're going to look at how do you use steps to solve stoichiometric problems. It's really important to have some kind of plan when you're looking at stoichiometric problems. So, first thing is you have to look at what are the steps. You have to read the problem. There's no way around that. Two, you want to look at what do you know and what don't you know. Make sure you write down the chemical equation if they haven't provided it for you. Make sure you balance it. I've had students that turn into problems that unfortunately are wrong because they forgot to balance it. And then lastly, just do the math. Okay, so typically with a stoichiometry problem, notice that you start off with a given. You convert it to moles of a given, and that's usually typically used with molar mass. And then you have moles of unknown. You're going to use mole ratio. Remember that it's that fraction using the coefficients that I talked about. And then eventually you get it to the correct unit that you want. Here we go. So we have 100 grams of methane that we burn in water, and we want to know how many moles of water do we get. Well, the first step is you have an equation and make sure it's balanced. And once again, I told you you wanted to start off with mole ratio. I'm sorry, not mole ratio, molar mass. So here we have 100 grams of methane, and this is the molar mass of methane, which is CH4. And when we do that, notice that grams cancel out and you're left with moles. So you can't stop there because that's just moles of methane. You then have to take it and divide or multiply it by the mole ratio. And notice that we are just using the coefficients that are part of the equation. There's an understood 1 in front of here, and then there's a 2 there. Notice that the desired moles is on top. The moles we're trying to cancel out are on the bottom, so that we're left with moles of water. Okay, here we have nitrogen reacting with hydrogen, and we want to figure out how much ammonia do we get. So the first step is, once again, we have a balanced equation, and we're going to take the mass of hydrogen. Notice it's H2, okay? It's diatomic. Once again, we're going to use the molar mass, and the molar mass is going to help us cancel out grams. Now, we're not done. We have to use mole ratio. So here is an understood 1 in front of nitrogen, and then 3 moles in front of hydrogen. Notice that the desired moles is on top. The one we're trying to cancel out is on the bottom. But we're not done. That would convert it to moles of nitrogen. We want mass of nitrogen. So notice that we multiply it by the molar mass of nitrogen, and it's N2. Okay, don't do it just by 1 nitrogen. And that gives us mass of nitrogen. Okay, if you did the same thing for ammonia, which is NH3, and I'm not going to show you the whole problem for that, you would get 31.53 grams of ammonia. Okay, now sometimes we have things that are not in the solid state or the liquid state. We're talking about gases. So because of that, we're going to use volume instead. Volumes are typically easier to measure when you're in the laboratory. So we could actually say at standard temperature and pressure, and I'll talk about that in class, what is standard temperature and pressure. Nitrogen will react with 62.1 liters of hydrogen, giving ammonia. So we could take that same reaction that we had in the previous slide, and we would just multiply it by volume ratios. Instead of mole ratios, we're talking about volume ratios. And notice that whatever that amount of hydrogen in volume, we're multiplying it by a volume ratio instead of a mole ratio. And once again, we are using the coefficients that are at the beginning of each substance. And notice that we essentially want these to cancel out. And it essentially gives us the equation 41.4 liters of ammonia. Okay, here's another problem where we're looking at sodium reacting in water, and we have added hydrogen gas, H2 again, and our product is sodium hydroxide. So once again, we need a balanced equation. We're going to take the volume of the hydrogen, and notice that we are going to multiply it by a mole ratio here. So we're going to say that for every moles of hydrogen, we have 2 volumes of sodium. Now, this is another standard that we need to look at, and this is the standard for every mole of any gas. It's equal to 22.4 liters, and what that does for us is actually cancels out liters, so that we're left with just moles. And notice that liters cancel out, moles cancel out, and once again we multiply it by the molar mass of sodium, and that gives us 16.7 grams. Now, you could do another equation where you have molecules, or remember particles. We're talking about the size of Avogadro's number. They want to know the volume of nitrogen dioxide that forms at STP. Remember, nitrogen dioxide was that nasty toxic gas that we produced in one of our labs. Here we have a balanced equation, and we essentially take the amount of molecules that they are giving us, and we essentially multiply it by Avogadro's number. Notice it's 1 over 6.02 times 10 to the 23rd molecules, and that gives us the moles. Okay, here's another one where we have volume again, and this is propane actually. This you can find in your local hardware store, the tanks that people buy for gas grills. So here we have carbon or propane reacting with air to form carbon dioxide and water. So we have a balanced equation once again, and we want to calculate the amount of oxygen. Now notice oxygen is on the reactant side. And remember, STP is standard temperature and pressure, and once again I'll talk more about that in class. Here we have the volume that they gave us, and we're going to multiply it by a volume ratio. So we're left with liters in the product. So 5 is the coefficient of oxygen, and 1 is the coefficient of propane. So when we do that, we're essentially left with volume of oxygen. Now they want to know mass of water. Once again, we have to bring out our constant that I told you about. So here is volume of propane, and we're essentially converting it to liters of water, and we are using this coefficient, or not coefficient, but this constant. For every mole, it's equal to 22.4 liters, and that will cancel out liters, so that we're left with moles. And moles cancel out once we multiply it by the molar mass of water. So it ends up to be 227 grams of water. Okay, so in summary, we are using starting material or maybe product material to predict how much our reaction contains. But before we even start doing that prediction, we have to make sure we start with a balanced equation. We use mole ratios, and these mole ratios are based on the coefficients that are in front of each substance. And we can use volume ratios in place of mole ratios when we're dealing with gases. Lastly, we use these mole ratios. They're kind of like the dividing factor, the center part of most equations, and that's how we can get mass from moles.